Hello, this is our week 5 lesson on cryptography course, and in this lesson we are going to do some math. As we said before, a Boolean function is a function that maps n bits into a single bit. So suppose that our n is equal to 3, then all these 3-bit sequences that we are going to have 0, 0, 0, 0, 0, 1 and so on. So we have written down all possible combinations of 3 bits. So our last bits are x1, the bits at the middle are x2 bits, and the first bits are x3 bits. Now let's define some Boolean function for which we are going to calculate the truth table. Suppose that our Boolean function is given by f of x, which is equal to x2 plus x3 plus x1 multiplied by x3. Now we are going to substitute the real values to this formula. If we have all 0 inputs, then we are going to have a 0. If we have values for 0 for x2 and x3 and 1 is equal to 1, then we are going to have 0 plus 0 plus 1 multiplied by 0, which gives us 0 again. If our second bit x2 is equal to 1, then we are going to have 0 plus 1 plus 0 multiplied by 0, which is 1. Next, we are going to have x2 is equal to 1 plus x3 is equal to 0 plus x1 is equal to 1 multiplied by x3 is equal to 0. So if we calculate this expression, this is going to give us 1, and so on. We calculate the value of the function f of x for each possible values of x1, x2 and x3. So this is our truth table which we calculated for this given Boolean function. Truth table is also usually denoted by f. So this is how we calculate our truth table. Now let's assume that we don't know the algebraic normal form of a function. To calculate the algebraic normal form of a function from the given truth table, we can use an matrix. As you remember from the previous lecture, the formula for calculation algebraic normal form was the vector of coefficients was equal to an, matrix an, multiplied by truth table. So this was our formula for determining the vector of coefficients C. So now recall that the matrix an of the dimension 1 was equal to 1. To perform this matrix by vector multiplication, we need a matrix of size 8 by 8. The first element was 1. To expand this matrix an, we rewrite the matrix itself into third, fourth quartile, and the second quartile was filled by 0. We expanded 1 by 1 matrix to 2 by 2. For the next expansion, we use this A2 matrix and rewrite it to third and fourth quartiles, and this third quartile should be filled with 0. We filled the third quartile and fourth quartile, and this quartile we are going to fill with. So this is what we obtained after expanding the matrix 2 times. Now we are going to rewrite this matrix to this third quartile and fourth quartile, and this second quartile is going to be filled by zeros, and we obtain the matrix of this form. The only thing we need to do now is multiply it by this vector of truth table. The obtained result of this multiplication we are going to reduce modulo 2 as it is shown in the formula, which gives us this vector of coefficients. Now if we have a closer look, this value of the truth table, this value was calculated when all the input values were equal to 0. Therefore, we can assume that this coefficient corresponds to the case when all the values of x1, x2 and x3 are equal to 0. We have only one such coefficient, which is a0. The next value of our truth table corresponded to the value where only x1 vector was equal to 1. Other two bits were equal to 0. So the corresponding coefficient must be a1, since if we look at the general formula for algebraic normal form, the coefficient for x1 was equal to a1, and so on. So to write down an algebraic normal form, we use only those values of x for which this corresponding coefficient is equal to 1, since otherwise if these coefficients are equal to 0, this is going to cancel the value of corresponding x's. So now we have the value of a2, which is equal to 1, the value of coefficient a3 is equal to 1, and the value of coefficient a13 is equal to 1. So our algebraic normal form for a function given with this truth table is equal to x2 plus x3 plus x1 and x3. So we obtained the same algebraic normal form from which we have calculated our truth table. The second method for calculation of algebraic normal form of a Boolean function from its truth table was by using butterfly algorithm. As you remember, in butterfly algorithm, we first need to consider two consecutive bits. So we divide our truth table to 4 subsequences, and to calculate the first bit, we need to just rewrite the bit as it is 0. To calculate the second bit of this substring, we need to XOR these two bits, which gives us 0 again. For the second subsequence, we rewrite this first bit, which is 1, and for the second bit, we XOR these two elements, which gives us 0. And so on. This is 1. This XOR will give us 1. Rewrite the element 0, XOR these two elements 1. At the next step, we are going to divide our sequence to two subsequences by 4 bits at each. Now we are going to rewrite these two bits as they are 0 and 0. To calculate these two bits, we need to XOR this bit with this bit, which gives us 1. To XOR this value, we are going to XOR the fourth bit with the second one, which gives us 0. Using the same logic, we rewrite these two first bits, and for these two values, we are going to XOR the third bit of substring with the first bit, which gives us 1, and to calculate this value, we are going to XOR 1 with this one, which gives us 0. At the last stage, we cannot divide this vector anymore because we have 8 bits. So we rewrite these first bits as they are. So we have 0, 0, 1, 0. To calculate the last 4 bits, we need to XOR this bit with this bit. This XOR gives us 1. To calculate this value, we are going to XOR this bit with this bit, which gives us 1. Next, we XOR the 1 bit with again 1 bit, which gives us 0. The XOR of last 2 bits result in 0. If we continue this algorithm, then we are going to rewrite all these values and no bits are left for XORing. Therefore, at this step we stop. Now, if we look at the coefficients, then we obtain the same algebraic normal form as we did with the first method for calculating INF. That is, we have the coefficient A2, the coefficient A3, and the coefficient A13 being equal to 1, which gives us the formula where we have x2 plus x3 plus x1 multiplied by x3. So this was the second method for calculating the algebraic normal form from the truth table. Now let's calculate the Walsh-Hadamard transform for a given Boolean function. As we remember from the previous lecture, for calculation of Walsh-Hadamard transform we need the polar form of the truth table, which was given by f cap. To calculate f cap, we map zeros to ones and ones to minus ones. As we know from the previous lecture, the formula for computing the Walsh-Hadamard transform from the Walsh-Hadamard matrix was given by this equation. That is, we need to multiply the Walsh-Hadamard matrix with the polar form of truth table. In our case, with n being equal to 3, the size of this polar form of the truth table is 1 by 8 bits. That is, if n is equal to 3, we have 2 to power n possible n-bit sequences. In our case, n is equal to 3. Then we have 8 possible 3-bit sequences. So the length of our truth table is 8 bits. We need our Walsh-Hadamard matrix to be 8 by 8. We know that H1 matrix is just 1. To expand this matrix, every time we rewrite the Hadamard matrix of the previous size to the first, second and third quartiles of the matrix, and at the fourth quartile we rewrite the value of bits in there. So our general formula looks like this. So using the same logic that we used to expand the matrix AN, we have expanded the Walsh-Hadamard matrix. Now we have 8 by 8 Walsh-Hadamard matrix. To calculate the Walsh-Hadamard transform, we are going to calculate this matrix with the polar form of truth table. However, this time, unlike the calculation of algebraic normal form, we are going to do all the calculations over real numbers. That is, we are not going to take the modulo 2. So if we calculate 1 by 1 plus 1 multiplied by 1 minus 1 multiplied by 1 and so on, and sum all these values, we are going to end up with this vector, which is our Walsh-Hadamard transform. So as we can see, the values of Walsh-Hadamard transform are either zeros or real numbers, and these numbers can be both negative and positive. So the Walsh-Hadamard transform of a Boolean function given by x2 plus x3 plus x1 multiplied by x3 is 0, 0, 4 minus 4, 0, 0, 4, 4. Now let's try to calculate the Walsh-Hadamard transform vector by using the butterfly algorithm. The logic behind the butterfly algorithm is the same as we saw at the calculation of algebraic normal form. First, using the same logic, we need to divide the polarized truth table into subsequences. So we have 2 elements, next 2 elements of polar form, and next 2 elements, and final 2 elements. To calculate the Walsh-Hadamard transform, we need to write the sum of 2 elements as a first element of new vector, which is equal to 2, and the difference between these 2 elements is the second element. So 1 minus 1 gives us 0. Again, at the second substring, we add these 2 elements, which gives us minus 2. Next, we subtract the second element from the first one, which gives us minus 1. Minus 1 is equal to 0. Again, minus 1 plus 1 gives us 0. Minus 1 minus 1 gives us minus 2. Adding these two elements result in 0. Subtraction of this element from this element gives us 2. To calculate the next vector, we are going to divide our obtained vector to two subvectors. Now, the calculation is done by adding these two elements, which gives us 0. Now, we subtract this element from this element, which gives us 4. Adding these two elements, we obtain 0. Subtracting this element from this element gives us 0. Let's do the same calculation for the second part of our vector. The sum of these two elements is going to give us 0. The difference between these two elements is 0 again. The sum of these two elements will give us 0. Subtracting this element from minus 2 from this element, so this element is subtracted from this element, gives us minus 4. And at the last step, first two bits are defined as a sum of elements. We sum this element with this element, which gives us 0. The sum of this element with this element gives us 0 again. Sum of this element with this element gives us 4, and summing this element with this element, we obtain minus 4. Next, for calculation of last 4 elements, we are going to subtract one element from another. So we subtract this element from this element. The result is 0. We subtract this element from this element, which results in 0 again. Subtracting this element from 4 gives us 4 minus 0, 4, and subtracting minus 4 from 0 gives us plus 4. Thus, we obtained the same Walsh-Hadamard transform vector as in the previous case. Thus, if we compare the obtained Walsh-Hadamard vector with the obtained with the previous method, we see that the result is the same. So, we have calculated the Walsh-Hadamard transform vector from polarized truth table of the Boolean function by using two methods. In addition to algebraic normal form, truth table, and Walsh-Hadamard transform, we define some other properties of Boolean functions, such as degree, linear and affine functions, weight of a function, distance between two functions, correlation between two functions, autocorrelation and nonlinearity. So let's start with defining the degree of a function. So we define the algebraic degree of a function as a number of variables in the longest terms. In our example, the longest term is x1 multiplied by x3, so degree of our function is equal to 2. If we had no terms with multiplication, then we would call such a function as a linear function or affine function. Now let's consider the difference between linear and affine functions. If we look at this Boolean function, we do not have a multiplication between bits. So in general, this function can be called as a linear function. However, here we have a term 1. Therefore, this function is called an affine function, as opposed to this function where we don't have this plus 1 term. So the difference between linear and affine function is given by this constant term. If we have a constant term, then the function is called an affine function, and if we don't have this constant term, then the function is called a linear function. The next property of a Boolean function is its weight. The weight of a Boolean function is defined by the number of non-zero elements in its truth table. So if we consider our example, we have 1, 2, 3, and 4 non-zero elements. So the weight of our Boolean function is equal to 4. Next term we need to define is the distance between two functions. The distance between two Boolean functions is defined as the number of bits where truth tables of these functions do not match. For example, suppose that we have two Boolean functions f and g with the given truth tables. So if we look at the bits which do not match, we have these two bits which do not match, these bits, and that's all. So we have 3 bits which are not equal. So to calculate the number of not matching bits, we can simply take their XOR, and this XOR will give us 1 for bits which do not match, 1 and 1, and for similar bits we have XOR being equal to 0, as in case of zeros and in case of ones as well. If we take the sum of all bits in the resulting truth table, this sum is going to give us the distance between two Boolean functions. That is, the formula for a distance between two Boolean functions can be given in this form. One interesting property of a distance is that distance between an affine function and its corresponding linear function is always a maximal distance, since if we calculate the truth tables of affine and Boolean functions, due to this one, the output bits are going to be the complements of each other. Therefore, the distance between a affine function and its corresponding linear function is always equal to 2 to power n, depending on the number of input bits. For example, if we have 3 bits, x1, x2, and x3, the length of truth table is going to be 2 to power 3, and for these two Boolean functions, the distance is going to be 2 to power 3, which is 8. Another function that we need to define is the correlation between two Boolean functions. Correlation shows the degree of relationship between two Boolean functions. Let me explain the difference between distance and correlation by an example. So to calculate the correlation, we can use this formula. So let's try to calculate the correlation for two functions for which we defined a distance. So in our previous example, the truth table of a Boolean function f was given by 1, 0, 1, 0, 0, 1, 0, 1, 1, and the truth table of a Boolean function g of x was given by 0, 1, 0, 0, 0, 0, 1, 1. As we can see, we need to calculate the polar form of the truth table. So let's calculate these polar forms, which will be equal to -1 to power 1 gives us -1, -1 to power 0 gives us 0, -1 to power 0 again gives us 0, and continuing this way, we are going to obtain this vector. Calculating the polar form of truth table for the second Boolean function, we are going to end up with this expression. So now let's calculate the multiplication of these two vectors, which gives us -1 by 1, -1, -1, plus 1, 1, -1, 1, -1 by -1 gives us 1 and 1 again. So then summing up these elements in the vector, we obtain 2, which is the cross correlation between functions f and g. If we have a closer look at the cross correlation function, then actually we calculate the number of elements where x is equal to g, which are these elements, this, and these 3 elements, and the number of these elements is equal to the number of all elements minus those elements where elements are dissimilar, and we know that the number of dissimilar elements is defined by our distance function. We can count the number of similar elements by extracting the distance between two Boolean functions from the total number of elements in our truth table, which is 2 to power n. So next, to calculate the cross correlation, we saw that from this number of similar elements we need to extract the number of dissimilar elements, which is the distance between these two functions f and g. So all that we have said before we can express by this formula, and it means that we can express the correlation between two Boolean functions in terms of distances between these two Boolean functions, and the correlation is going to be equal to 2 to power n minus 2 distances between f and g. There is another very interesting property of correlation function. Suppose that our function f is an affine function and our function g is its corresponding linear function. Then we are going to end up with all -1 elements in this vector, which is going to give us the maximal possible negative correlation, which is -2 to power n. And if we calculate the correlation between the function with itself, then we are going to have a maximal positive correlation, which is 2 to power n. The term autocorrelation is defined as a correlation between the function and its shifted version.